Hi everybody, welcome to Math with Ace or Stats with Ace. Today as we're talking about binomial distributions. And in order to perform calculations with a binomial distribution, your situation needs to meet the binomial criteria. And in order to do that, you need to meet the acronym that I like to use, which is BINS. And B stands for binary, I stands for independent, N stands for the number of trials is fixed. And S stands for the success probability is also fixed. Now, later on, we'll be doing examples where we're determining whether a situation is binomial or not. So we'll be verifying that these four criteria are met. But binary means that there's only two possible outcomes. You either have a success or a failure. Think of binary code, 0, 1. There's only two numbers. Computer programming started out, we're dealing with binary numbers. So success or failure. You got it or you didn't. Think about go fish. Do you have a 4? You either have a 4 or you don't. Now there's a bunch of different cards in a deck of cards, but to make it binary, you need to define success or failure. Think about a bag of M&Ms. M&Ms has a variety of colors, but you could turn it into not red, green, blue. You could say, what's the probability of getting a blue or not? So making it binary. Independent means that one trial does not affect another. So for instance, what you do one time does not impact another time. Now, if you had a deck of cards and you were talking about the probability of getting a heart or not, in order for that to be independent, you need to be drawing the card with replacement. You need to put the card back in so that you still have your 52. As soon as you start doing something without replacement, you've changed your sample space and your probability is no longer fixed and they're not independent. The number of trials means I draw a card 5 times. I roll a die 10 times. I take 4 free throws. It is not trials until success. That is geometric. How many shots until I make a basket? That is geometric. Binomial has a fixed number of trials. And then the probability is fixed. It doesn't change. Remember, if you draw a card, you take away a card, you're changing your probability to be out of 51 instead of 52. So you have to make sure that those 4 criteria are met. And in order to do this, we have to think about what's success, what's failure, what's probability of success, so on. So for this first example, it says at ABC College, the withdrawal rate for an elementary physics course is 30% for any given term. This implies that failure, dropping that they would not withdraw, is 70%. So you have success or failure, you either withdraw or you don't. Now, what is success doesn't necessarily mean it's a good thing. It just means what is considered the probability that we're talking about in this situation. So withdrawal rate is 30%. That's what we're told. 70% students stay in the class. So what would be, since we are given this information, let's say we ignored this information and we are just given what's in pink, then a success would be withdrawal from the course. Now, as a teacher, I don't see this as a success, right? I don't want a student to withdraw from a course. But in the situation that is defined, that is success. And the probability of success is 30%. The probability of failure is 70%. And notice that 30 and 70 add up to 1 whole. All right, let's check. Next example. Suppose you play a game where you can either only win or lose. The probability that you win any game is 55%. The probability that you lose is 45. Each game you play is independent. You play the game 20 times. X is the number of wins. Is this a binomial distribution. Let's try that again, highlighting. Is this a binomial distribution? We need to check our 4 criteria. B, I, N, S. Is it binary? Let's check. Do we have success and failure as our only options? So the first sentence says, suppose you play a game where you can only either win or lose. Win or lose, that's 2 options. This is binary, we're good to go. I stands for independent. Whether you win or lose one time does not impact the game the next time. In this situation, I was told each game you play is independent. So yes, one game does not impact another. N is a number of trials is fixed. So I play the game 20 times. Yes, N equals 20. Excellent. S, the success probability is fixed, meaning the probability doesn't change. The other piece of information I'm given is that the probability you win any game is 55%. So this is a yes, and the probability equals 0.55 or 55%, however you want to write it. So B, I, and S all meet the criteria. Yes, this is a binomial distribution. All right. A coin has been altered. So that the probability of flipping a head is only 0.25. This means the coin is no longer fair. I'm more likely to flip a tail. The coin is flipped 5 times. Each flip is independent. Let X equal the number of heads in 5 flips of a fair coin. What is the probability of getting more than 3 heads? Okay, so we need to check and make sure this is binomial before we calculate binomial probabilities. If it's not binomial, we need to use some other sort of calculations. And there is a formula for binomial calculations that involves calculating the number of combinations possible for how likely something is to occur, and then calculating each individual piece. However, we're not going to be using a binomial calculator on a TI-84. In our class, the way that I'm teaching it, we're going to be using Statlet, the free applet that allows you to calculate binomial distributions. So that's what I'm going to be sharing with you in just a moment. But I want to check that it's binomial. The coin is flipped each, so I have independent. I'm looking for a number of heads, so I either have heads or tails. It's binary. I'm flipping the coin 5 times. That's a set number of times. And heads has a probability of 0.25. So in this situation, N is 5. That's the number of times that I'm flipping the coin. And the probability is 0.25. That's the probability. So I am binomial. So what I can now do is I can go to Statlet and use the applet to help me calculate these probabilities. Okay, I've gone to the website statlet.com, and this is a probability situation I'm dealing with. So I'm under the probability tab, and if you notice, we have normal distributions, discrete random variables. There's a series of videos on discrete random variables that I've created, and then we're dealing with binomial distributions. So I'm going to click binomial distributions, and I am prompted to enter my sample, the number of trials, which was 5 in this situation, and the probability. Now at the bottom, I'm given some options here, but I can't activate these options until I plot my distribution. And what happens is I get a picture of what this distribution would look like for my 0 to 5 times if the probability was 0.25. I'm also given the mean and the standard deviation. So the mean of a binomial distribution is found by taking n times p. There's a formula for that. The standard deviation is found by taking the square root of n times p times q. I will write those down on our notes and come back to this. But it's already calculated for us in Statlet. Now at the bottom, you'll be asked, calculate the probability of with the drop down, or between. So I can do a lot of calculations. And if you select this box right here, you actually have the option to calculate exactly, less than, at most, at least, or more than to answer the question. And our question was, what is the probability of getting more than 3 heads? So I select more than, I put the number 3 successes, and then I select go. The region on the graph is highlighted for me to show you the numbers that are more than 3, and then I'm given a probability as a percent. So the probability of having more than 3 heads was 0.0156 or 1.56%. Okay, I'm going to go back to our other screen to write that down and show you the formulas. I'm also going to record that the mean was 1.25 and that the standard deviation was 0.968. And I'm going to show you where those calculations come from, just for reference. Okay, as you can see here, I've written the probability that x is greater than 3, that is, x being the number of heads is more than 3, was 0.0156 or 1.56%, which was the calculation that we got in Staplet. Now, we were given that the mean was 1.25 and the standard deviation was 0.968. And I told you the formulas. The formula for the mean of a binomial distribution is found by taking the number of trials times the probability. And so for our situation, that is 5 by 0.25. So 5 times 0.25 is in fact 1.25. That does verify what we were given. The standard deviation is found by taking the number of trials of 5 times the probability of success times the probability of failure. Now, the probability of failure is written as Q, and that's found by taking 1 minus P. And 1 minus P, that's the probability as a decimal, is 0.75. So if I took my calculator and I said square root 5 times 0.25 times 0.75, I would get that the standard deviation is equal to 0.968. And that is also verified here. Okay. Let's look at our next example. Approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. And in a statistics class of 50 students, what is the probability that at least 40 will do their homework on time? Students are selected randomly. So let's record the information that's necessary. Is it binary? So let's see. We are talking about students do their homework on time, not in time. On time. All right. So they either do their homework on time or not. Yes, binary. We're going to define success as doing their homework on time. Are they independent? Well, we are told that they do their homework independently. Yes. Number of trials, is that fixed? So in a statistics class of 50 students, what's the probability that at least 40? So in this case, there are 50 students. We are dealing with a set number of 50. And the success, is there a probability of success that doesn't change? 70% of statistics students do their homework on time. Yes. So P equals 0.7. So I want to know that at least 40. In notation, that's saying the probability that X is at least 40. Is that more than 40 or is that more than equal to? At least means I include the value. So the probability of more than 40 means I need 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, and 50. So I'm going to pop back to Staplet and use that to help with this calculation. Okay, back to our situation here. We now have 50 as our N, and our probability was 0.7. Notice that our distribution changed. We are now centered around 0.7 of 50. So at the number line, you have number of successes. Well, 70% of 50 is going to give me 35. So if you notice, the highest bar is right over 35 because that is the most likely to occur. Now what I want to know is, what's the probability of being more than 40? It's all of these. Or at least 40. It's 40, 41, 42, 43, 44, and so on. So what I would do is I calculate at least 40, and I select go. So all of those options, the probability of being at least 40 is 7.89%. Now, how many ways can each of these occur? So when you're doing the binomial calculation and you're dealing with combinations, you have to figure out the combination of how many ways you can get 40 right. Is it students 1 through 40, students 1 through 39 and 41? How many ways does that occur? Times the probability of getting it right and the probability of getting it wrong. So there is quite a formula. You can do it by hand. We're not going to do that in my class. So we're going to use our technology tools and move forward. So the probability of getting at least 40 students who turn in their homework on time was 7.89% or 0.0789. If 70% of the time is what we're dealing with, we would expect around 35. So having more than that is a little bit less likely. Okay, we're going to do one more video of examples calculating mean and standard deviations with binomial distributions. Thanks for watching.